right, so here we go. Here's what we ended up with. And I'm going to bring the delta x over to the other side. I'm going to have the delta area from A to x over delta x equal f of c. Okay? Okay. Now here's what I'm going to do. I'm going to take the limit as delta x goes to 0. Okay? This is what we did when we did the derivative and we wanted to find the slope of the tangent line. What you did is got an approximation in terms of delta x, and then you let delta x go to 0. When you let delta x go to 0, the slopes of those secant lines became the slope of the tangent line, the derivative. When I let my delta x go to 0 here, okay, that interval is going to get narrower and narrower. And what it's going to enable me to do is set up an equation that I can solve where I can find the area under the curve. And that solution is what we're looking for. So here's what I'm going to do. I'm going to take the limit as delta x goes to 0 of both sides. Okay. Now, you guys didn't do that today or yesterday or sometime at all. You didn't do this proof, did you? No. Okay. That's probably because she's about 10 times smarter than me and realizes that doing a proof is ridiculous and a waste of time.
Yeah.
Oh, well. All right. But I have faith. Okay, let's look at the right-hand side first. I'm going to let delta x go to 0. I'm going to ask you this. What happens to f of c as delta x goes to 0? As that interval gets narrower and narrower, as this line here gets pushed this way to the left, the c is going to be in there, okay? But what happens to f of c? What does it get closer and closer to becoming as delta x goes to 0?
1.
Not necessarily. Who said that? F of x is correct. Wow! Because it gets pushed over there. And it's got no choice, okay? This is f of x. It's getting pushed over there. It's going to get closer and closer to being f of x. The limit will be f of x. That's exactly right. Wow, very good, Vitaly. Wait, have you seen this before? Wait, you looked it up on the internet beforehand? No. No. All right. On the left side, this one's a little bit trickier. On the left side, here. I want to know what this limit is as delta x goes to 0. Now, let me say this, though. The numerator of that is the area from a to x. The numerator is some function of x, okay? It's the area from a to x. That's what that numerator is, okay? The denominator is delta x. What is the limit of that delta area from a to x, which is some function of x, over delta x as delta x goes to 0? What is that limit equal to?
0.
Could be 0. It's possible.
But wouldn't it always be because of delta x's?
Yeah, delta x is going to 0, but so is the change in area going to 0 as well. They're both approaching 0. Okay?
So it's an area from A to X?
No, not yet. We're headed there, but it's not there yet.
I'm confused.
Okay, go ahead.
I don't get it. As it goes close to 0, you're finding f of x. What is that f of x going to give you, and how will that?
This f of x
how
here?
will it give you the area?
Well, this f of x doesn't give me the area. This f of x is the function. I'm saying the right-hand side of this is the function.
So you're looking for the function that will give you the area.
Well, eventually I'm going to get the area.
Okay.
Eventually. But right now I need to know what the left-hand side is. If I were to replace the area from a to x, if I were to replace that with a y, okay? If I were to replace it with a y, I would have the limit of delta y over delta x as delta x goes to 0. What is that limit equal to?
Delta y as it goes to 0, x?
What is it?
As delta y goes to
As delta x goes to 0, I want to know what the limit of delta y over delta x is as delta x goes to 0. Could be infinity, could be 0, could be 1, could be 2, could be 3, but it always is one thing. There is one thing, a definitive answer. What?
Derivative? No. After the third try, sure.
It's the derivative. It's a definition of a derivative. That's what a derivative is, okay? It's the limit as delta x goes to 0 of the change in that function in the numerator. Call it y, call it whatever you want. It's whatever that is over delta x. That's the derivative. Okay, whew. It's the derivative. What do I have here? I have a differential equation to solve, okay? I've got a differential equation. I'm going to solve it by moving the dx on the other side. And do what? How do we solve differential equations? What do we do now to both sides? Yes, we do the integral. We take the antiderivative or the integral. Here's what we have. The integral of the derivative. What do these do? They're inverses to each other. We'll get the area from a to x is equal to the integral of f of x dx. Okay? Now, what is this equal to? That's equal to some function, some antiderivative. Call it capital F of x plus a constant. Okay? Where, what's true about capital F of x? What's its derivative equal to?
Little f of x.
Yes, thank you, Trent. Little f of x. All right, we're almost there. We're almost there. We're getting there. I don't need another piece of paper. I think I can do this all at once. Okay? Okay. One thing we should know. What's the area from A to A?
0.
0. Very nice. This will enable us to solve for our constant. Okay? Let's check it out. The area from A to A is equal to f of A, replace the x with A, plus C, and that's equal to 0. What I'm doing is replacing this x with A, and I know that this area from A to A is 0. This enables me to solve for the constant. This tells me that the constant is equal to the opposite of f of A. Just subtract it. Okay. Oh boy, here's what I have right now. Okay. I have this. I got to go to another page. The area from A to x is equal to the integral of f of x dx. And to show that we're going from A to B, we put in these limits, A to B, and so far what we have is f of x, the c we just showed was minus capital F of A. Okay? That's what we just did. Finally, the area from A to B, replace x with b, is equal to the integral from A to B, f of x dx, is equal to, replace the x with b, capital F of b minus capital F of A. That's a QED. Okay? Here's what we just did. We just proved that the area under this curve from A to B, as long as the function is continuous and differentiable, is equal to the integral of this function, the solution to a differential equation, which is evaluated at B, evaluated at A, take their difference. Last class, we showed that the area is the limit as n goes to infinity, as the delta x goes to 0, of the sum of f of x sub I delta x, I goes from 1 to n. This is called a Riemann sum. Okay? What we did, we divided up that area into rectangles and let the delta x go to 0, let the number of rectangles go to infinity, got this Riemann sum. What this gives us is this. Okay, this is as math as it gets this whole semester. Okay, I have one other proof we're going to do a little bit later on, but not today. But this is it for the math part. The rest is applications and cranking out results, which is engineering part, which is what most people would rather do. Okay, so here's what we have. Since the area is equal to this integral and the area is equal to the limit, we have this, the integral from a to b, f of x, which is f of b minus f of a, is equal to this limit as n goes to infinity of the sum of the f of x sub I delta x. And this is huge. This is big. Why is this big? Because if we have a problem to solve and we can set it up as a limit like this Riemann sum, if we can set it up like this, we can solve the problem with an integral. And there are lots and lots of problems that can be set up this way. Anytime we have a problem that can be solved by dividing up into little tiny pieces and summing up all the pieces, we can solve with an integral. Okay? And the next chapter, the whole chapter is doing just that. We're going to be finding volumes of solids of revolution, surface areas, arc lengths, centroids of lambdas of constant density, fluid pressure, work done by a spring. All of these very basic things can be set up and solved this way. So this is critical, okay? This is critical. Okay, let's do a couple applications here. Let's do some integrals, okay? So here's what I'm saying. If we want to find the area under a curve, do an integral. So let's do one. Let's do the average value and the area under y equals e to the x. Let's go from 0 to 1. Yeah, I'd rather go to 4. Make it 4.
You like 4.
I like 4. It's a nice perfect square. It's a nice number, you know. It's not my favorite number. My favorite number is 28, but
Why?
it's a perfect number. Okay, perfect number because the sum of its proper divisors, 1 plus 2 plus 4 plus 7 plus 14, is equal to 28. The first perfect number is 6. 1 plus 2 plus 3 is 6. First one. Second perfect number is 28. Third perfect number is like 396. Then it's 4,028. They all go like this. It's really amazing. 6, 8, 6, 8. They all end in 6, end in 8, end in 6, end in 8, end in 6. It's amazing how that works. Plus, it's my professor number. I'm MM28. But I knew it was a perfect number, so that was it. Okay. But anyhow. Okay. Here's what I want you guys to do. Okay? 1. Find the area. 2. Find the average value. Okay? 3. Find the C where the average value occurs. I want you to do those 3. You know what? I think we are going to go on some. We're going to go on some because.
On the substitution?
Yeah. Which is.
Might as well, because we're.
I know. I don't usually do it that way because the substitution thing is so important. It's so critical to being able to do the rest of the course. I don't usually do it, but I feel like I really have to now.
Probably not going to have class Monday. So.
I know it. That's another reason why I think we should do it. So I'm going to do it. I'm going to go on to the next section. This section, really, the homework is pretty simple. It's just doing just what I just gave you here. You don't have to do any proofs or anything like that. You know what I mean? So the homework shouldn't be that bad. It's the next section that's critical. But I wanted to get that math proof in there. See, if you like proofs like that, you should consider being a math major, because that's what math majors
The
do.
thing is, there would be no purpose for math if there wasn't a use for it.
That's not true. I disagree.
So true.
That's not true. That's not true.
Imagine it, what's the point of counting, like, for example, back in the day, counting your herd of sheep, you know?
That's useful in itself. You're going to sell the herd, you need to know how much food you're going to. I mean, that's useful in itself, but math for its own sake is good. There are things that have no applications that I know of that are good in and of itself.
For what?
For beauty, for truth, for advancing human knowledge.
Math is very important.
No, I'm not saying it's not. I'm
It's
just saying
important
that it's only
application-wise,
important
but it's also important not for its applications, but just for the human brain. The human mind is capable of these amazing proofs, these beautiful, elegant proofs. I mean, it just shows you what the human being is capable of. I think this is
Once
critical.
again, that's for something.
There you go.
It's not philosophy.
It is, and it's kind of religious too. Why do we have such magnificent brains? I mean, it wasn't just for survival. It could be a religious thing. Why do we have these incredible brains capable of such things where we don't really need to be that smart to survive?
God created.
Well,
No, there you go. See,
we
there's
didn't evolve
possibilities
to
here.
learn math.
What's that?
We didn't evolve to learn math. We just do it because we
didn't evolve.
Yeah, but my point is, we do these incredible things that we didn't need to do to survive. If you go purely by evolution, well, I don't know. Hey, listen, let's not get into that. I'm just saying math is awesome. That's what I'm saying. That's my bottom line. I'm just saying math is incredible.
We're all of a sudden in an English class.
Well, yeah. That's true. And I should stay away from such things because that's not my expertise. Okay, how we doing?
I got sidetracked with the philosophy.
I'm definitely lost.
Well, you should be able to find the area.
Could you give me a hint where to start?
Start by finding the area by doing the integral of that function from 0 to 4. Perfect. Integral of e to the x is e to the x. Okay? Because the derivative of e to the x is e to the x. So the integral is also that. You want from 0 to 4. And so, yeah. Yeah. Oh, that's it.
Yeah.
That's the average value. Well, no.
Yes.
You got one more step. Boy, this is really good. What's e to the 0? It's a to the 0.
doesn't change.
That's the answer for the average value. The,
Oh, look at this.
this is e to the 4 minus e to the 0, 1. That's the area. This is the average value. The last thing is to find the c. So f of c, which is going to be e to the c, has to equal this. This is kind of weird what it's going to come out to be. How do you solve your c?
Is that your time, Council?
Is yeah, these are inverse operating. If you take the natural log of e to the c, you're going to get c.
Minus.
Yeah, that's it.
Thank you.
You had it though. You had it. That was really good.
It's close.
Well, you were right there.
E to the z. No, I didn't say math wasn't useful though.
No, I know you didn't. You never said that.
I think you were saying that.
What's that?
I think we need to kick him out.
He didn't say it wasn't useful, but he said where it's useful, that makes it important. Where it's not useful, it's probably not as important in those areas.
It's true.
Basically, is what he
It's
said.
kind of true, though. I mean,
Yeah.
Art is an art, I understand, but.
Oh, yeah, art. What about art? Is
Okay.
art important at all, or what? You
Is
want
it gonna
poetry,
give-
art,
is it gonna give
literature?
you- Is it gonna give you the food if you're gonna be hungry? How's art gonna help you?
Oh, well, hey,
Where I'm
well,
at, where you
there's
can-
more, there's things other than eating and drinking and whatever else you do.
Well, I'm saying if it's, certain things, they're not as important in life where, you can't live without food.
I agree with that. I
I'm just
can't not
just brought an
disagree with
example
that.
up Where you can use a math equation, how you're gonna throw that rock into that coconut.
Okay, on that level, you're right, But we have evolved to the point where
We don't
that
need
we're beyond that. It's a Maslow basic needs kind of a thing,
Most jobs.
Actually, in a lot of countries, there's still hunger and.
Oh, yeah,
So-
yeah. And they don't have the people doing this theoretical mathematics, because if you're hungry and you need food, you're not gonna sit down there and do some theorems. I agree with you.
I'm saying art.
You never know.
You never know, that's true. Well, the reason the Greeks did so much with geometry, because they had a leisure class, they had other people gathering all the stuff for them. They didn't have to worry about it. They had the time to sit there and think these things out and do these
And make
things.
up stories and myths and.
And whatever they wanted to do.
Exactly.
All right, how we doing? All right, let's go. Find the area. The area, okay, from 0 to 4 is equal to the integral from 0 to 4 of our function, e to the x. And the integral of e to the x is e to the x. From 0 to 4, substitute in 4, substitute in 0, e to the 0 is 1. That's the exact area under that curve. Okay?
Wait, where did I want to go? Sorry.
E to the 0
Oh,
is
it's
1.
Oh,
Okay?
Never mind.
That's all, no big deal. The average value is 1 over b minus a, 4 minus 0, okay, times the area. Well, we just found the area, so it's 1/4 e to the 4th minus 1. That's the average value of this function, okay? What is this? This average value is this height of that rectangle, whose area is the area under the curve. That's what this average value is. It's this height right here, okay? It's the value you would get if you took 1,000,000 values from 0 to 4 at random, found e to those values, added them all up, and divided by 1,000,000. You would get a number very close to this. And it should be pretty much dead on, right on. What c value gives us this? Well, we have to find the c, where f of c, e to the c, is equal to 1/4 e to the 4th minus 1. Well, how do you solve for c here? What do you have to do here to solve for c? Take the natural log, away. You take the inverse operation to exponentiation, which is taking the natural log. So you take the natural log of each side. The natural log of e to the c is c. C would be the natural log 1/4 e to the 4th minus 1, whatever that is. Okay? Any questions on that? Okay.
Make it look
Is
so
that-
easy.
What's that?
So how come you make it look so easy?
Because it essentially is. And plus,
What's his job?
it's my job, and I've been doing it for a very long time. A very long time.
How's your first semester, like, teaching?
What's that?
How was,
My first semester teaching?
like, first year, first semester?
My first year of teaching was not so hot. I considered being an actuary and going down to Mass Mutual and signing up for an actuarial thing. I was teaching at a high school, East Middle High School, and of course, being a first year teacher, I got not the best classes. And I'll tell you, it was stressful that first year. But after that, it was better and better. It got better and better. And then when I came here, it was like going to heaven. Okay?
Compared to high school?
Compared to high school, yeah. Teaching high school, and it was a good high school too, but compared to high school, coming here.
Yeah,
was-
high school
College is
scholars.
a little different. A little
And I had good classes there too,
I can agree
but,
with that.
what's that?
I can agree with that. I go to high school.
Yeah, yeah.
I wanted to, did you like the actuary thing?
When I was in 8th grade, I considered it. It's the only time I considered my first year of teaching and on 8th grade. I sent about 50 letters to life insurance companies all across the country requesting information on their actuarial science. And I got all these things from all these life insurance companies when I was in 8th grade, and I was considering it. That would be my second choice for a career. My first choice was always teaching math, though, ever since I was a little kid. And I really haven't regretted it, except for those couple of times I thought about doing the actuary thing. The actuary thing is still really good. It was really good in the 70s. If you're going to be a math major, in the 70s and 80s, it was like rated the #1 career profession in this country. Pay is outstanding. Atmosphere is great. You get a challenge. You got a mental challenge. You meet people. You design pension systems for like nuns and groups of people, and it's really a good job. Except for now, a lot of it is turnkey. A lot of it is computers that just generate these pension systems, and the need for actuaries has decreased considerably. So it's not as valuable as it used to be, but it's still a great job. And if you get to the right place, the right company, you go to Mass Mutual, they'll give you time, they'll pay for education, and it's a good thing. It's a good thing. All right, how are we doing? I'm going to go on to 5.5, okay?
In the back had a question.
Oh, somebody had a question.
Someone in the back right
Jeff?
now.
Did you have a question?
I just told you not to move it yet.
Oh, you did? Okay. Am I all right now?
You're fine.
Okay. All right, here we go. Let's go on. This next section, 5.5, is very important, okay? Very important. Right now, we have integrals. Let me give you the integrals that we have right now. The integration forms we have are these. X to the n plus 1 over n plus 1 plus c. N is not -1. We have the integral of e to the x plus c. We have the integral of, did I do 1 over x, the natural log? I think I had to mention it because it was part of a homework. 1 over x dx, is the natural log of x. Actually, it's the natural log of the absolute value of x plus c, okay? That way you keep it positive here because you can't take the natural log of a negative number. We have the integral of sine x is a negative cosine x, the opposite of cosine x. We have the integral of cosine x is a sine x. And where did we get these integrals from? We got them from Calc 1, believe it or not. Why is this true that the integral of this is this? Because the derivative of this function is x to the n. Why is the integral of e to the x e to the x? Because the derivative of e to the x plus c is e to the x. What's this? Why is this integral the natural log? Because the derivative of the natural log is 1 over x. The derivative of this is this. Derivative of this is this. I believe I also gave you a secant squared to be tangent. And I may have even given you a secant tan. Okay, which is secant. How do we know this? Because the derivative of secant is secant tan. I don't think I gave you the integral of tangent yet because that's coming up. I'll prove that. I believe this is what we have right now as far as antiderivatives or integrals, all as a direct result of having derivatives from Calc 1. Okay? What we're going to do tonight, right now, is to generalize these. Okay? Like this. I'm going to do this. Let's say we have to do 2x plus 1 cubed. Okay? 2x plus 1 cubed. Now, we could integrate this. We could integrate this how? How could we integrate this at this moment? What's that?
Without using substitution.
Say that again.
Just boiling.
Boiling it out, exactly right. Multiplying the whole thing out. But what is that? That's a binomial expansion. we could do that by doing it this way. Cubing this, okay? Plus 3 times this squared, okay? It'd be 12x squared plus 3 times this plus 1 dx. You're going to have to trust me in this, okay? When you cube this, this is what you get. And then integrating it term by term, okay? Because we can do an integral of a sum by doing the sum of the integrals. And we would get 8x to the 4th over 4, 12x cubed over 3, 6x squared over 2, x plus c.
Wait, so what did you just do?
What I did is integrated each one of these parts, each one at a time. And when I did the x cubed, I did x to the 4th over 4. That's what this says. If you've got x cubed, the integral is x to the 4th, add 1 to the exponent, and divide by that new exponent.
Where did
Okay.
why don't you have it over there?
Say that again?
Why don't you have the n plus 1 over there?
I do. Oh, well, I divided it into 8 to get 2. I have a 4 down here into 8 to get 2.
Oh, 4 divided, okay.
Yeah, 8 divided by 4. And I just took care of that as I went along. Okay.
For each one you would have a c also.
If you want, but you know what? When you have a C here and a C here and a C here and a C here, guess what? What is C plus C plus C plus C? Still a constant. Okay?
That's still c.
Just one constant. That's all you need. It's the one constant.
You wouldn't have like 3c
No.
and 4c.
Nope. Okay, that's one way to do that problem. But here's the thing. Let's suppose you had something like this. You know, theoretically, you could do it by a binomial expansion. But boy, that would be a genuine pain in the neck, okay? You'd have to know those binomial coefficients.
Well, Pascal's triangle, right?
Yeah, you could do a Pascal's triangle and get the binomial coefficients that way. That would be possible. Not practical, though.
So we're doing
Okay.
from the sum
So we need something else. Here's
sum
what.
equation, right?
What's
The
that?
sum equation.
No, what we'll need is a substitution. What we're going to do is change this integral by changing the variable. We're going to do this. We're going to let some variable u equal 2x plus 1. That's the quantity that's raised to the 9th power. Let's find the derivative of this. What's the derivative of the 2x plus 1? What's the derivative of 2x plus 1?
It'd be x squared.
No, not the integral, the derivative.
Oh, the derivative.
Is going to be
X. 2.
2. Derivative is 2. So du, I'm going to solve for du, 2 dx. Now here's what I'm going to do. I'm going to change this integral into an integral in terms of u. Watch what happens. I have a u to the 9th. Now, I've got a dx here. What I'd like to do is get this in terms of u as well. To get this du involved, what I'm going to do is multiply this by 2. Okay, I'm going to multiply this by 2 and multiply by 1/2. I'm allowed to multiply outside the integral by a constant. What I've done is multiplied by 2 and by 1/2. In effect, I've multiplied the integral by 1. I haven't changed its value. This 2 I'm leaving in here. Why? So I can replace it with du. Okay? Now watch what I've done. Look at what I've done here. By multiplying by 2 and by 1/2, I changed this integral from this form into this form. Now, what's the integral of u to the 9th du?
Is that derivative? So the derivative, it's just a regular number?
Yeah, it's just our old form. It doesn't matter if I have x to the n dx or u to the n du or y to the n dy, as long as they agree. What do? You add 1 to the exponent and divide. In other words, I can now apply my rule from before by making that substitution. Okay? I get this as an answer, u to the 10th over 20 plus c. What's u? The u is 2x plus 1. Okay? I don't have to multiply it out. As long as I can get this du right here, with at most the introduction of a constant, which I did, I can change it to this form and do the integral immediately by using the rule that we had from before. And how do we know this is correct? What do you do how do you know that this integral is correct?
Find its derivative.
Find its derivative. Yes, that's exactly right. Let's take the derivative of this expression. What do we have? We have a u to the n. This is what you did in Calc 1, right? You had a derivative of u to the n. What's the derivative? The derivative is the 1/20th, the constant. The derivative of u to the n is n, u, n minus 1, times du dx, the derivative of 2x plus 1, which is 2. The derivative of the constant is 0. I have a 20 over 20. They cancel out. I get 2x plus 1 to the 9th, which is exactly what I started with.
Magic.
It is magic. So, here's what we're going to do. When we have an integral, what we're going to try to do is to get it into one of those forms so we don't have to do something like that big giant multiplication. Let me give you the generalized integration forms in terms of u. Here we go. And then we'll do some examples. Okay. Here we go. So, we have the integral of u to the n. Okay, du is equal to, I don't know why I drew that line there. Okay. U to the n is equal to u to the n plus 1 over n plus 1 plus c, and is not negative 1. Where u is some function of x. I just used that. We have this integral. E to the u du is equal to e to the u plus c. These are identical to what we just did, except now I'm using u's for x's, where u is a function of x. We have the integral of, let's go in the same order I have here, 1 over u du, natural log absolute value of u plus c, integral of sine u, negative cosine, integral of cosine u, sine u, secant squared u, okay, integral of secant squared is tangent, and the integral of secant tan is secant. Let's use them, see what we got. These are what I want you to know right now. We're going to add to this list. We have a few more to add. Not a heck of a lot more to do, but we have a few more to add during the semester. Okay? What's that?
Tangent.
Yeah, we're going to have the integral of tangent. It's going to be a natural log. We have the integral of secant, which is a natural log secant plus tangent. And then we got the inverse trig functions to do too. All right, so we're going to have to do those. We got 3 inverse trig functions to add on there. And we're going to have cosh, sinh, hyperbolic trig functions to add on there. But those aren't very difficult at all.
So is Calc 2 mostly about integrals?
Almost all about
Just
integrals.
everything integrals?
Yeah. Chapter 1, what we're doing now is just setting up that integration process, doing some basic integrals. Chapter 2 is the application of these integrals to solve problems. Chapter 3 is using different techniques to solve integrals that we can't solve with these basic techniques. But Chapter 4 is totally different. It's on infinite series, and it's totally different. Yes?
How many chapters are we doing now? Is that the whole book?
That's the calc. Actually, there's another chapter wedged in there. We only do one section. We do the logistics function. So there's actually 4 chapters we do with another section. So we actually do 4 chapters, though. We have 4 tests. We have 4 tests. Same as calc.
Same as last year?
Same as last
Not
year.
last year.
Yeah, last year.
Or whatever it was. Seems like, well, it was last year. And then count 3, we have 6 days. There are six chapters covered.
It's online in the summer, right?
It's online in the summer. Yes, it is.
Is it the first session or like the second session?
The whole summer.
The whole summer?
But it's online. So if you are
You want to cheat?
super fast, if you want to what?
If you want to cheat.
You don't have to cheat. No, it's not cheating. It's out there. If you finish it, it starts June 2nd, say. I don't know, whenever it started. If you want to finish it by June 3rd, fine, do it. You've got 6 tests to do. You got a final exam, and you got 6 labs to do.
Why, all of it will be available?
Oh, yeah.
It's not like you're gonna give like one test?
I won't dribble it out. It's all there.
Oh,
Okay? You think you can do it?
well, I'm not gonna do it fine in a day.
All right. Whatever.
Might take a month.
A month would be good. Some people can do it. Some people do it. Others never finish it, and they get an F.
They just
1/3 of the people get an F.
And they never log back on or something.
They log in the first time in July sometime. They do one test maybe, and then I never hear from them again. So, but most people do okay. We get a lot of people from UMass doing it. They're good. They're good. I mean, you get people from Stick, but I also get people from this college in Vermont a lot. I can't remember now. Some college in Vermont, Norwich University. I get a lot of those people for some reason. I'm not sure why, but I get those people.
Don't they have their own, don't they like?
No, they don't. They don't have it online, and evidently, whoever teaches Count 3 at Norwich in the spring is really, really difficult, and like fails everybody. So they all end up taking my distance class in the summer. I think that's what happens. That's my best explanation that I can for that. Either that, or it's my reputation as as out there.
It's probably a tropier.
It could be something like that, where it's very difficult to pass the course, so they end up taking my course, which is fine, which is good for me. Okay, let's do some examples of using these generalized integration rules, okay? This is what we have here. Now, let's do something like this. How about e to the 3x dx? Okay? Now, what you're going for is to take this integral and by an appropriate substitution, end up with one of these integration forms. Okay? That's what you want to do, end up with one of those forms. Because once you get it to look like one of these forms, you can do the integral. So, to get this to look like one of those forms, what should I let u equal?
3x.
3x.
Why?
Because I want to get to that form e to the u. Okay? That's the form that I'm aiming for here. I'm going to let u equal 3x. The du dx, I'll write it out that way, is 3. Du is 3 dx. In order to make the replacement, I need to get this dx to be 3 dx so I can replace it with du and get to that form of e to the u du. Can I get there? Sure. Just multiply by 3 and by 1/3. Okay? I'm always allowed to multiply inside by a constant and its reciprocal outside because I'm multiplying by 1. I'm always allowed to do a constant. Yes?
What is that over the E? Is that a 7 or
Where are you?
whatever you just down one? What is that over the? Is that even an E?
That's an E right here.
What's over it though?
3x.
Oh, okay.
And this, I still don't like this screen here. Okay. That's what it is. Okay, now, what do I have? 1/3. The integral. E. 3x, that's u. 3 dx, that's du. What I've done, by the simple multiplying by 3 and by its reciprocal 1/3, I've changed the integral from this into one of our integration forms. Okay? And what's the integral of e to the u? E to the u. And what's u equal to?
3x.
3x. You should get back to x's, okay? If you start with x's, you should get back to x's. Done, okay? The integral is done.
So all you did was put the u back
Yes.
to the x?
Yep.
And where did the du disappear from?
This symbol, together with the du, say find the function whose derivative is this. They work in tandem, okay? They didn't go anywhere. They say, this is what you do. This is what it means. Find the function whose derivative is e to the u. That function is e to the u. That's all it is.
So it just cancels those out?
Basically, yes. Yes, you can think of it that way.
Okay,
That's
so
fine.
du and that.
And the integral symbol, yes.
They cancel out.
That is correct. They're inverses to each other. That's a
When
good
they
way to
mul-
look
When
at
they
it.
multiply by each other, is that correct?
Yes, yes.
Or am I getting?
Well, you're getting a little bit too far out there, but, because in effect, you don't really multiply them, okay? But the symbols, what they mean is find the function whose derivative is that e to the u. They are inverse
Would
operations.
they be able, well, see, why I'm asking is,
Mhm.
if you had something like them on opposite sides of an equal sign, they wouldn't be able to cancel
No,
out.
no, you have to have it just in this form like
In this
this.
form, okay,
Yeah.
that's what.
Yeah. Okay, suppose you had a definite integral here. Okay, let's do a definite integral. Let's do this one. Let's do the integral of sine 2x dx. And let's have x go from 0 to pi over 4. Okay, let's do this one. Okay, now, what form are we going for here? What form do we have here?
Would be cosine.
Well, the answer is going to be cosine, negative cosine, but what form do we have? We're looking for the integral of sine u. That's what we're looking for, okay? I'm going to put it in that form. What's u in this case? 2x. What's du? 2 dx. Du dx is 2. Du is 2 dx. I'm going to bring the dx over. What I'm going to do, in order to make this replacement, I'm going to multiply by 2 and by 1/2. Okay? So I have this, 1/2, the integral of. Now, you got to be a little bit careful here. You've got two possibilities. One possibility is leave these limits of integration, which are x limits, leave them, but specify that these are x limits. And then convert this to sine u du. When the limits of integration are different from the variable that you're using, you have to specify that. I have another choice, though. I could have changed these limits of integration to be u limits.
Can you just do that? Just say it's.
Yeah, I can do that. Here, let's do it right now. Okay, so I can either do it this way or I can do it this way. When x is 0, what's u? 2 times x, u would be 0.
0.
So I could have done it this way, change the limits. So when x is 0, u is 0. When x is pi over 4, what's u? Pi over 2, thanks. 2 times x, it's 2 times this, which is pi over 2. Okay? I could do it either way. We're going to find out with the more complicated integrals that we do later on, we're going to be better off changing the limits of integration here to be u limits. Yes?
Would you change the u's like cosine or?
Well, right now I'm going to integrate it.
Oh.
Let's do it. Let's do it.
Yeah. Okay.
Yeah, no, I'm
You're
not.
saying that's it.
No, not yet. Well, no. Yeah, it's not it.
When we're finding the u and the gu, that's just we're just getting that form so we can actually change it to the regular, the first one.
That's exactly right. That's exactly right.
So we have to memorize those formulas.
Yes, you do.
Okay.
Yes, you do. You got to memorize those forms. No getting away with it. Okay. What's the integral of sine u? Negative cosine. I'll take the negative out front. Cosine u. Okay. But I have x limits here. And if I'm going to keep these x limits, I'm going to have to get u back to x. What's u equal to? U is equal to 2x. Thank you, Melissa. Now my limits agree with the variable. Let's substitute in. Cosine of 2 times pi over 4, that's the cosine of pi over 2, minus the cosine of 0. Okay, is everybody okay? What?
What was the point in like changing the x to u for like the intervals? If you're just not even going to use it.
Well, I did use it. I had to do it to get to an integration form that I could actually do the integral. See, I can't do this integral the way it is now. I don't have that form. I had to change it to this u form.
Yeah.
My choice was whether to change the limits of integration or not.
So shouldn't you just not change it, because then when you went down further, you still use pi divided by
Yeah, and then went back to x's
pi
again.
divided by
You can do it either way. I'm going to do it the other way too. You can decide.
Okay.
Okay? And I'm telling you that later on, it's going to be better doing it this other way, changing the limits of integration as we go along. What's going to happen later on is we're going to have to make 2 substitutions. We're going to start with an integral. We're going to make a substitution to get to another integral. And then we have to make a second substitution to get to yet a third integral. And as we go along, we're going to change the limits of integration, because sometimes it's going to be difficult to get back to x's again. You're going to have to trust me on that. That's coming up. That's a little ways away. Yeah, go ahead.
So that pi over 4, you did the minus the cosine pi over 2, so you multiplied it out by the negative half first, am I correct?
No.
Or,
When I put in the pi over 4, I multiplied it by 2.
oh, okay, my bad.
No, that's all right. Go ahead.
I still don't get it, because see how we use pi divided by 4?
Yeah.
Then what was the point of changing x equals pi divided by 4 to u equals pi divided by 2? If we're not going to use it, we use pi divided by 4.
Okay. What I had to do with my original integral, which I could not do in that form, I had to change it to this form so I could do the integral.
Yeah.
Okay. So I'm saying you got 2 choices. Keep your original x limits,
Okay.
but do the integral in terms of u and then go back to x's, or change the limits to u limits where right now I don't have to go back to it, okay?
How did you change it though without that 2?
Say what?
How did you get that pi over 2 without, because you just looked ahead, is that what you did?
No, I put in pi over 4 in for x and multiplied by 2.
Well, I got that part, but
Oh.
like the one that she's asking about.
This other one over here?
Yeah, how'd you get that pi over 2?
This pi over 2 I got from over here when I let x equal pi over 4, put pi over 4 in for x and get
So
u.
it's pretty much you're doing the same thing. just-
Yeah, it's really a minor kind of thing. At this point, with the integrals this simple, it really doesn't matter. Do it any way you want. I'm telling you this, though, when they get more complicated, you want to change the limits as you go along. But here, you'll see, you'll get the same answer and everything here. What's this equal to? Negative 1/2. What's the cosine of pi over 2? Okay, 0. What's the cosine of 0? 1. We get 1/2. That would be our answer. Okay, that's our answer here. This integral, okay, is 1/2. Let's do it from here now. This is where I went back to x's again. Now, this one I changed the limits of integration. I changed them to u limits. That's what I've done. And now, let's do the integral. What's the integral of sine? Negative cosine. But now I have u limits, so I substitute them right in. Bless you.
Bless you.
Cosine of pi over 2. Okay, minus cosine of 0. What do you get here? What's the cosine of pi over 2? We just did it. It's the same exact thing. We get 1/2. Okay? This is not a big deal. When the limits of integration, either keep x's and go back to x's, or go to u's and evaluate in terms of u. We'll do another one. Let's do another one. Okay. All right, that's okay.
Are we done?
With that one, yeah. I'm going to do another one. I've got to do another one because I'm definitely not going to leave you guys like this because there's too much confusion out there. Confusion reigns out there.
Let's do one we do our.
Yeah.
and then
Yeah.
we get to leave, right? After that one.
Ooh, I don't know about that.
Well, it's not gonna.
Gessner votes for that. He says, yeah, let's get out of here. Go ahead. What's that?
I just have to show something.
Okay. Oh, you got a problem there for website?
Yeah.
Yeah, you can do that. Want me to do one like that? But that's not even a U thing, that's just, you want to rewrite that as 3x to the negative second. Well, you could do it that way, but now you're still gonna have to separate this over this minus this over this. You gotta separate. And you end up with this, yeah, you're gonna end up with
Why are
that.
you so smart? Why are you so smart?
Yeah, but you're gonna change that over x squared to x to the negative 2.
I'm a little confused.
Yeah, I'll do it. I'll do it. All right, Gessner has a question here. Let me do the one he has in front of him. You're going to run across it, but this let's do it. What are the limits of integration?
That's 8 and
3 to 7?
8.
8. And what's the 3 over x squared minus 1? With a problem like this, what you always want to do is get this in the right form. 3 to 8, 3x to the negative second minus 1. You want to rewrite these like that. Okay? You're going to run across this. Now, what do we have? 3, what do? Add 1 to the exponent. And plus 1. Divide. Okay. Minus, what's the integral of 1 dx?
X.
X, very nice, thank you. From 3 to 8. I would rewrite this as 1 negative 3 over x minus x. Okay, this negative 1 I would bring up front. X I would bring down here. 3 to 8. It's just messy, this problem. Put an 8 in there, you get negative 3/8 minus 8. Minus. Substitute in 3, you get negative 3 over 3, which is negative 1, minus 3. Oh, jeez. This is another reason I don't like WebAssign. They get, it's just yucky, that's all. So what do you got? You got this thing, negative 3/8 minus 8 minus, that's a negative 4, so it would be plus 4. Negative 3/8 minus 4. Negative 3/8, go for 8 over 8, 32/8. Seems to me you're going to get negative 35/8. Try that. What do they want? Decimal with 3 decimal places or something? All right.
Are we gonna have any of them on the other side where the derivative is equal to the substitution on the side?
Say that again?
Are we gonna have any on the other side where the derivative is outside of the argument used?
I'm not sure. What do you mean?
X to the 4th times x to the 5th minus 1.
Oh. Like so?
Yeah. The
Yeah.
power of any power of 1.
Gotcha. Well, yeah, I got to do something like this.
Yeah, okay.
Yeah. All I've done so far is just the constants, and now we're going to have to. Here's what Damien is saying. Let's suppose you have this problem to do. Okay. Let's put this up there like this. You could do this. You could do this by multiplying that thing out. Okay. Cubing that x to the 5th minus 1 and multiplying each term by x to the 4th and integrating term by term. You could do it. Not the best way. What you could also do is recognize this is a u to the n form. If you let u equal x to the 5th minus 1, what's that derivative? What's du equal to?
du. In
Yep.
that case is x to the 4th, right?
5x to the 4th. Okay, that's a derivative. dx. Okay. All right. Let's start. Let's make sure we're okay with this.
No. 5x to the fourth, what do we get? Where'd you get that? I said x to the fourth.
Taking a derivative.
Take the derivative of x to the fifth. The 5 comes out front, x, reduce it by 1. That's what we had from Calc 1.
Oh, okay.
Now, I have an x to the fourth dx. What I would like is a 5x to the fourth dx. I can easily get this by multiplying by 5 and by 1/5. I can do this, 1/5, 5x to the fourth dx. Okay? I can multiply by 5 and by 1/5. I've multiplied by 1. Why? Why do such a thing? Because now, what do I have? I have 1/5, the integral of u cubed du. This is u cubed. The 5x to the fourth dx is my du. By doing that, I've made the problem much easier. Okay? Go ahead. Ask away. Okay. What I'm saying is, if you can look at this and see, oh, there's x to the fifth minus 1. If I let that be u, the du is going to be 5x to the fourth dx. I already have an x to the fourth. All I need to do is multiply by 5 and by 1/5 to get that 5x to the fourth. And once I do that, I can replace that with du, and I have a u cubed du form. And once I have that, hold on, let me just finish this. I have 1/5 u to the fourth over 4. And what's u? X to the fifth. So it's x to the fifth minus 1 to the fourth over 20 plus c. And that's my final answer. Go ahead.
So you're finding the derivative of the u. That's the way you find that?
Yes.
You get 5x to the fourth.
Yep.
From there, you're trying to simplify it, so you put a variable of 1/5 in the front.
What I'm trying to do is take the integral that's given and end up with one of those integration forms, a u to the n form that I have. And I can do it as long as I have a 5x to the fourth. I only have an x to the fourth right now. I need to get 5 of them. So multiply by 5 and by 1/5 to get the 5x to the fourth that I need.
So then you find that u, and then you simplify it.
I made the substitution, u cubed du, and then I integrated it. Now, Trent.
If you had something that wasn't just one exponent apart, like if you had x to the fourth to like x to the seventh minus 1, would you then have to multiply
Yes.
it by like 5x squared?
No. Let's do it. This is an excellent question. Okay? Let's suppose you had this instead. Okay? Now, you've got x to the seventh minus 1 cubed. And you say, okay, this must be another one of those u to the n things where u now is x to the seventh minus 1. The du would be 7x to the sixth dx. We have a problem. Because what you're not allowed to do is multiply this by x squared and then multiply by 1 over x squared outside. You're not allowed to bring the variable outside. It changes the integral. This problem can only be done by multiplying this whole thing out. You can't do it as a u to the n form. Okay? Because I had the x to the fourth, though, I could do it. But if I have something else, I can't. What you're allowed to do is multiply by a constant and its reciprocal. That's what you're allowed to do. Okay. That's a good question, because what that means is if you have this integral to do, let's take a look at this integral. If you try for an e to the u form, where u is x squared, what's your du?
1 over x.
2x. I don't have it. Can I get it? No, I cannot. I cannot get it. This integral simply cannot be done. Okay? It cannot be done now, nor can we won't be able to do it the whole semester. Okay? We can't do it. It can't be done. Okay? We can't be done. All right? Calc 3, it can't be done. Calc 3, it can't be done. It simply can't be done. There's tons of integrals that can't be done. But there are very complicated ones that you could do now I'm going to show you one here. Let's take a look at this one.
I like the ones we can't do.
All right, watch this one now. I'm going to give you, this will be a beaut here, all right? Well, you know what? You may get them with coarse compass.
Well, Professor Burns, maybe this is your moment to shine by finding the integral.
Oh, well, there are a class of functions called ERF, error functions, that will do that thing. But there's a whole class of functions designed to do those things. We'll never be able to do them. This can't be done with elementary functions. Let's take a look at this one. Cosine x, and then I have sine x to the fifth, okay? Question is, can I take this integral and get it to one of our integration forms with at most the introduction of a constant? Can I look at this and get one of those integration forms?
Probably
Yes, I can, by letting u equal what?
S sin x.
Yes! Wow. Yes! Let u equal sine x. What's du?
Not sine x to the fifth?
No, not sine x to the fifth. Just the sine x. What's du?
Cosine x dx.
Oh, say that again.
What?
Negative cosine, that's what you said.
Cosine x dx?
Cosine x dx. Derivative sine is cosine. Integral sine is negative cosine. And you got to
Oh,
keep
it's
those
negative
straight.
sine.
Oh, so it's not negative?
Okay.
How about negative?
No, the derivative of sine is cosine. The integral of sine is negative cosine. Okay. What does this mean? This means I can change this integral to this. U to the fifth du. Cosine x dx is my du. I'm simply making a replacement for it. Now I have a u to the n form. All right, this is critical right here. You've got to be able to see this because this is fundamental kind of thing. You've got to see that there are integrals where we can take those integrals and make a substitution like this to arrive at an integration form that we have. Right now we have like 6 or 8 integration forms. We're going to end up with about 15 or so. But our quest, half the course virtually, is to take an integral that's given and change it into an integration form that we have. Okay, and most of the time it'll be stuff like this. Make those substitutions. So this is good. This is fundamental stuff right here. Okay. So, what do you think?
Can we finish that off?
Yeah, let's finish it. What's the integral of u to the fifth?
Would it be 5 minus 5 plus 1, right? 6.
Yep, u to the 6 over 6 plus c. And what's u? Sine x. Now, how do we know this is correct? Take the derivative. Let's take the derivative of this expression. It's a u to the n form. The derivative is, we got a constant 1/6. What's the derivative of this? 6 comes out, sine to the fifth times the derivative of sine. Okay, which is cosine. Derivative of a constant is 0. 6's cancel. We're left with sine to the fifth cosine. That's exactly what we started with. That proves that what we have is correct. Now, how are we doing on that? If you don't have this cosine, the problem is much more difficult to do. Okay? Because we have the cosine to serve as the du, it's not very difficult. It's pretty simple. In our third chapter that we do, we're going to do things like the integral of sine x to the fifth. We don't have the cosine. And what we're going to do at that point is manufacture a cosine to use as the du. And we're going to do that by splitting this sine to the fifth up into a sine x times sine to the fourth. And then we're going to take the sine to the fourth and write it in terms of cosines. And each of those cosines will be getting a sine to serve as the du. I'll tell you what, the trig that we're going to be doing, we'll be doing a lot of trig in that chapter in a few weeks, okay? Lots of trig. You're going to have to know the trig identities, Pythagorean identities, but you've got to know that sine to the fourth, sine squared, sine squared is 1, okay, 1 minus cosine squared, multiply it out. You guys know all that stuff?
Just forget it. You gotta remind us. I remember doing it.
Yeah, well.
That was a long time ago.
Yeah. All right, let's do, all right, here we go. Let's do,
Just one of those that,
all right, hey, if you want, what do you think? You think you're ready?
and then we go home.
Are you ready?
We'll see.
400.
We'll do it till we can do it.
What do you think, Jeff?
No.
I'm going to give you one, okay?
Okay, let's go.
I'm going to give you one. I'm going to give you a definite interval. You're going to come up with an answer, a single number, okay? Then you're going to raise your hand when you get this single number, and I'm going to check it out. 2, 4, 5. We got. I need 6 people. That's all I'm going to be asking for. 6 people to get it right. If you answer it and you get it wrong, you're out. Okay? I need 6 people with the correct answer. If we get 6 people, we're done. Okay?
Well, we're gonna be here for a long time.
If we can't get 6 people, then we do another one. Okay? And that second one, we'll make it a little bit more complicated, and more complicated, and more complicated.
And then we do assign one with just sign.
Yeah, all right. Well, here we go. Let me give you one to do. Let's do the interval from 0 to 1. And let's do, I'll make it pretty simple here. Let's do, all right, just do this.
Thank you.
We'll make it simple. When you got an answer, raise your hand. You got one shot at it.
It's a 4, right?
That's a 4.
Okay, just making sure.
Don't have to do it out, okay? You're going to have an exponent there, a number to an exponent, and you don't have to do it out. All right, we have an answer. Raise your hand. Let's say 6 people, okay. 6, okay. But these 2 guys are going to get a 2 for 1. So if one gets it right, we got an automatic 2. But if one gets it wrong, we get an automatic 2 wrong. So it works both ways.
You're talking about?
Yes. I don't mind if you kind of work together, as long as you realize it's
No,
both ways.
we're just using one calculator.
Yeah,
Yeah, you plug it in. Oh, yeah, that's right.
Okay, did I mention this? When you get the answer, raise your hand.
I'm guessing you want us to raise our hands.
Well, no, just take your time. Take your time.
You're rushing us.
I'm sorry. So this is 5, 5 as well. So you should be doing 5, 4, and 5, 5. Okay, Vitaly, you have an answer? Okay. Okay, I agree with this. Kind of. What is this number? What do you have here? Oh, geez, you did it as a decimal or something? Holy mac. You divided by 5? I'm going to have to say that this is not correct. What happened to this guy? So that's not correct, because we've got 0 for 1. He's one of our top guns. He's like our Tom Cruise.
Yeah,
you're right.
Chuck.
This one was a plus. this.
One over 30.
That's why I was confused.
Okay, when you have a definite
It's
interval,
okay.
there's no plus C.
Okay, so
You
it's
solve for C.
I get it.
There's no C.
So it's always minus x?
No, the integral of 1 is x. That's what that is.
Okay, so if it's plus 1 would be plus x?
Yes, it is.
Oh.
Okay.
7 over 30.
So it's supposed to be like a number, not like.
But that's okay. I'm going to give it. This is the correct answer as long as you just leave the exponent alone. Don't have to do it. You're going to have a number to an exponent. That's kind of big. Just leave it alone. Okay? We got 1. We got 1. Yes, you got it?
Okay.
We have 2. Nice job. We have 2.
Are you actually with the math?
Well,
No.
sort of. Oh, I said leave the exponent there. No, you guys have to do it. Is that what this is? Then I agree. We have 3.
Vitaly helped me with that. I messed a little bit.
Well, okay, all right. I'll give it to you, though. We got 3.
If you take that out.
It is kind of messy.
I didn't hear
Well,
Basically,
yes,
right.
I
You don't
yeah.
plus C, but that's the name.
Basta
Solve for C. And you're going to substitute in.
No.
All right, let's see what you got here. Oh, I'm doing 7. 0. You're gonna get this. 1.
4?
Yeah.
And that
I got that right.
Yeah. Well, that's why.
4. We got 4.
I did a different number, but I got the same.
Did different number?
Yeah, by accident.
He did it to the 7th, not to the 4th.
Ooh, this is not.
I messed that up.
I thought it was
Wait a minute,
7.
wait a minute, wait a minute, hold on.
The 1.
Which one?
Okay, where are you guys?
The exponent's a 4.
Okay.
It's a 4.
Then 7 times 5.
Because we had a 1 in that other problem you were showing me, that's where I next. We don't have a 1.
It's like, yeah.
You don't have this.
Wasn't right.
Yeah, but you make the substitution for u for
So
it.
does it not even need that?
No, it's u to the 4th, which becomes u to the 5th over 5, which you have. And then you went back to
Yeah.
x's
Damien,
again
I mean,
and substitute in.
for some reason I thought it was 4.
I thought it was 7.
I agree with
I
you.
stopped it.
Okay? You make that,
Is that a 4?
and you
Doesn't
end
make
up
sense.
1, 6, 0 to 1.
No, it does make sense. Like, you can like substitute it in, add that, so that you're only doing.
This is what you've got right.
Right,
The du is the 60W. That's what you've got right with the W's. But anyhow, that's okay.
No, it's not a W, it's a U, it's just,
All right, all
it's a
right.
big tail.
So now you integrate that, and you get this. From 0 to 1.
Got one ahead of time.
No, there's no plus C with a definite interval. Okay? So you get 1/30th. Now what's u equal to? U is equal to 6x plus 1.
Yeah, smart, because I got an A.
Okay, so now you get 1/30th, 7 minus, you put a 0, you get 1. That is your answer.
Could I, if I had done this,
You're totally
it
right.
would have been all right?
Yes.
Did you check mine?
I think we have 5. I think you guys are doing great.
I did 7, so mine was 7, not 4.
So everything else is the same. All right, so 8 over 8, and you substitute, yeah, but you haven't substituted in yet, but if you substitute in, you're gonna get it.
Alright.
Yeah, all right, we got 6. Unbelievable, how you doing?
Well, I thought it was a 9 at first.
Oh,
Then
well,
I
it does.
heard
See, you
someone
can't
say
see
it was a
either.
7. Then I changed it, and I heard it was a 4, so I just quit altogether.
I can't say that I blame you on that. All right, here, let me do it out.
It's the same process.
Yeah, it is the same process. Here's the deal. You look at this and say, okay, that's a u to the n form. I'm going to let u equal 6x plus 1. du is 6 dx. Can I get it? Sure. Multiply by 6 and by 1/6. I'm going to change this now. So it's 1/6 the integral. Now these are x limits. I could go to u limits. When x is 0, u is 1. When x is 1, u is 7. I'm going to go to, most people just went with x limits here. This is u to the 4th du. Okay? And people had this. This is really good. All right? 1/6 is here, u to the 4th du. Now, do the integral. What's the integral of u to the 4th? It's u to the 5th over 5. X is going from 0 to 1. All right, is there any questions on this? Everybody okay with this? Okay. Melissa, how you doing?
Well, I got confused why du was 6.
When you take the derivative of 6x plus 1, it's 6.
Oh,
Okay? So, now I get 1/30th. I have a u to the 5th, but I'm going to go back to x's. 6x plus 1. Where x is going from 0 to 1. I have 1/30th. Substitute in 1. You get 6 plus 1 is 7 to the 5th. Minus, substitute in 0, you get a 1. That is your answer. And that's what people had, too. And that was pretty good. All right, here's the deal. Homework. You should be doing 5, 4, and 5, 5. Now, from one day, who knows, okay? I have people telling me today we're going to get 2 feet of snow from Monday, and it's definitely not from Monday.
I didn't say.
I don't know. No, that was this afternoon. So I don't know what's going to happen. If we don't have class, we come back on Thursday. Just be advised that if we skip another Monday, though, we're going to have to extend these things and do more than one section or 2 sections a night.
We already extended it.
Yeah, we extended it today a little bit. I don't usually do those 2 sections at once. I usually just do the definitions. Anyhow.
You kind of need to do it at this point.
Yeah. All right. See you Monday or Thursday. Do 5, 4, and 5, 5.
You want to write?
Yes.
Running away.
I'm actually going. I'm actually kind of.
I don't want to do this.
That way.
Dude, you'll stop this. I know.
We have to have a
We're going to lose by 40, like they have to lose by 40.
No, plus C. You've already solved it. So you get this. The limits are 0 to 1.
Экзамен надо посидеть. Oh wait, you can't go anywhere.
You can't go.
Oh, it's still recording too.
Oh my gosh.